Here in section 24.4.6, we're going to finish up our discussion of circles and all of these little additional circle concepts by talking about spinning or rolling circles. There are a few different things that College Board occasionally, although we should say it's very rare that you will see questions about spinning or rolling circles. They will show up only once every few tests, but there are a few things that College Board likes to test in terms of spinning or rolling circles. We will say that some of this stuff, especially the stuff that we will talk about first, with this position and path of a point on a spinning or rolling circle, some of this stuff is based in unit circle trigonometry and graphing of trigonometric functions. You do not need to have learned that information yet in order to be successful on these questions. However, would it help to have gone through that information either in your sessions with your tutor or in school? Yes, certainly it would help. But again, you do not need that basis in unit circle trigonometry and graphing of trig functions in order to see and even understand clearly what is going on here. Let's start talking about a curve generated by the height of a point on a spinning circle. So here's what we are going to do. We are going to look at this point P, and we are going to track that point as this circle spins in a counterclockwise direction. So you can see from this arrow, we are spinning in this direction, and therefore point P will be moving around the circle like this, from point to point to point, starting here, and we will just go to this point here where P, which started on this horizontal radius, P will now sort of be at the end of this vertical radius here. So what's going on to the right here is we are graphing on an XY plane, although this isn't really an XY plane. It is a central angle and vertical distance from the horizontal diameter plane. In other words, when the central angle, let's take a look at this 30-degree bar. We can see 30 degrees here. And we can see from this dotted line, I'm going to zoom in here a little bit. We can see from this dotted line that the height there at 30 degrees on this, let's just call it an XY plane. This is X, this is Y. The height there at 30 degrees it corresponds to the height of point P above this horizontal diameter of the circle when the central angle is 30 degrees, that central angle being made up of this radius and the horizontal radius that P lies at the end of there. So again, we have this central angle in here that is 30 degrees. And when that central angle is 30 degrees, in other words, when the circle has rotated 30 degrees counterclockwise, we have point P being this height here, let me do that in green, this height here above that horizontal diameter, and that height corresponds to this height over here. If you look at 60 degrees, so 60 degrees, I'll do this one in blue, 60 degrees is here. And following this dotted line over to here, we can see that's the distance or the height of point P above the horizontal diameter when we have a central angle of 60 degrees. So between that radius and that radius, we have a central angle of 60 degrees. And when the radius is up here and point P is at the end of that radius, point P will be this height above, getting messy here, this height here above the horizontal diameter. And then at 90 degrees, when the central angle is 90 degrees, P will be all the way up here. And therefore the height above the horizontal diameter will be a radius length, right? That's the radius length. So there is that same radius length at 90 degrees. So again, all that we're doing here is we are at regular intervals. In fact, each of these intervals would be 10 degrees, 10, 20, 30, 40, 50, 60, and so on. At each 10 degrees, what we are doing is we are graphing the height or plotting the height of point P as point P rolls around the circle, or as this circle rolls and the position of point P changes, we are plotting the height of point P above the horizontal diameter of the circle. And what ends up happening, and again, if you have done work on graphing of trig functions, this should look very familiar to you. What ends up happening is we have the start of a wave curve. We have the start of a wave curve. So once again, as point P moves from being at 0 degrees to being at 90 degrees, in other words, as we move through the first quarter of the circle, we make a quarter turn, or we work through, we could even call this the first quadrant of the circle. P goes from a height of 0 to a height of 1 radius length above the horizontal diameter. Now, if we move into the second quarter of the circle, let's say the second quadrant of the circle, as the circle continues to turn, point P will move from this point up here to this point down here. And therefore, we will go from the point that we were at when we ended up here, which corresponds to this 90-degree central angle down here. And then, of course, the height of P will start to decrease. The height of P above that horizontal diameter will start to decrease until once again it reaches 0 when point P gets all the way over here. P is on the horizontal diameter at that point, which means its height above the horizontal diameter at that point gets back to 0. Remember that when point P is over here, that will correspond to 1/2 turn of the circle. In other words, a central angle of 180 degrees. That corresponds to this point over here where the height of P above that horizontal diameter is 0. So what happens here is we continue that wave curve. And now we have just traced out, that got ugly there, let me get rid of that. We have just traced out one peak of this wave curve. Still a little bit ugly, but I'm going to leave that one. Now, as we move through the third quadrant and point P moves from here to here, again, P is getting farther and farther away from the horizontal diameter, although now it is below, point P is below that horizontal diameter. So our heights are no longer above the horizontal axis over here, right? This horizontal axis, still that central angle measure. Let's do that. Central angle measure axis. So now point P, because point P is below the horizontal diameter of the circle, we have these lengths going below this axis. And once again, as we move through that third quadrant, we are continuing this nice, neat wave curve. And then as we move through the fourth quadrant, the distance that point P is below the horizontal diameter is getting smaller and smaller and smaller as we move back towards that starting point. In other words, we've gone a full circle, 360 degrees, and that is why we are completing one cycle of our wave. So we went up, hit a peak at 90 degrees, went back down, hit another 0 distance there, 0 distance above or below that horizontal diameter. Then we got down here to where we were at, what is that, a 270 degree central angle. And then when we moved back to 360 degrees, we got back to a height for point P of 0 above that horizontal diameter. So what is the point here? The point here is that when we have a point that is moving around a circle, if we graph at regular central angle intervals, remember we're graphing every 10 degrees, we are graphing the vertical distance of that point from the horizontal diameter, either above or below the horizontal diameter. What that curve will generate is a wave curve, also known as a sine curve. What we actually are graphing here is a sine curve. Again, if you don't understand that, or you have not done trigonometric functions graphed on the xy plane, that's fine. You don't really need to know that this is a sine curve. Just think of it as a wave curve. By the way, the cosine function will also be a wave curve, although it will look slightly different from the sine curve. We do not need to go into those details right now. Now, what might a question that is testing this concept, what might that question look like? To be honest, it might look exactly like what we just went over. You might be told that there is a certain point on a wheel, or it might be that you're dealing with a Ferris wheel and you're talking about a specific car on the Ferris wheel. I don't know if they call them cars, but that's what I'm going to call them. A certain compartment on that Ferris wheel. And you might be asked about the height of that car, either above the horizontal diameter of the Ferris wheel or even above the ground. And generally what you need to know is that as that car goes around the Ferris wheel, the height of that car above the ground will trace out a curve, or will create a curve that is one of these wave curves. We have a example here that this might be similar to what College Board might do on one of these questions. So we've got this point T at a certain point on this tire, and the tire in this case is moving in a clockwise direction. So as this tire rotates, point T will start moving down the tire. Point T will be in a fixed location, but as the tire rotates, obviously point T will start to move around the tire, or appear as if it's moving around the tire. And what that means is that, the height of T above the ground, when at our starting point, when T is here, will be this height. And then as T starts to move down the tire, as the tire starts to rotate, as this car or whatever this tire is attached to starts to move along the ground in this direction, the height of T will start to decrease until the point where T is actually on the ground. And then past that point, as the wheel continues to rotate, the height of T will start to increase again. That's what's happening right here, until the point at which T hits or gets to the top of the tire. That would be this peak point here. And then of course the height of T above the ground will start to decrease, and eventually it will hit the same height at which it started when the wheel has done one full turn. So that's what one of these questions might look like. They might actually ask you what the graph or what the curve would look like if you were plotting the height of some point above the ground or above the horizontal diameter of some wheel as the wheel spins. If it is hard to really hammer home some of these points with these static images, with images that don't move. If you are interested in seeing an animation or a moving picture as to how this curve actually gets generated, you can always Google sine curve rolling circle, or rolling wheel wave curve, some combination of those words, and most likely you will get either some videos or some animated GIFs or GIFs, however you want to pronounce it, of a point moving around a circle and the curve that is being generated by the height of that point. On the next page, we're going to talk about something that we are going to admit right off the bat. We have never seen College Board test this particular sub-concept, this particular circle sub-concept, but we do sense that it's something that College Board could test if they wanted to, or maybe is aching to test. So we are now talking about the path traveled and the curve generated by a point on a rolling circle. So we're no longer talking about the height of this point above or below the diameter of the circle, or above or below the ground that the circle is rolling on. What we're talking about is the path that this point will sort of trace out through space. In other words, as the circle moves sort of horizontally to the right, what path will this point P take? So what we've got here is we've got point P at the bottom of this vertical radius. Here the circle has made 1/4 turn, 1/4 turn here, so that the radius has now gone from being from going straight down. Now the radius is going left. That's where that radius would be after 1/4 turn. Point P still at the end of that radius. After a half turn, the radius would be pointing straight up. Point P at the end of that radius. After 3/4 of a turn, the radius would be heading right or pointing right. Point P at the end of that radius. And then finally, a full turn, one full revolution. Point P will be back where it started at the bottom of that vertical radius. And what we should be able to see, or what we should roughly be able to conceive of, is that point P has traced out this, what looks like a circular shape. It's actually not a circle. This is known as a cycloid, And then when the wheel goes through another rotation, you will see yet another cycloid, and that will happen over and over and over again. So again, the path that point P will appear to travel, like if point P were lit up and this wheel were spinning very fast, were rolling very fast, you would sort of just see these bolts of light that, again, kind of trace out these somewhat circular paths. Those are known as cycloids. Rolling circles and distance traveled, we have to know the relationship between revolutions, in other words, the number of full turns that a wheel makes as that wheel rolls along a road or some flat surface, the relationship between the number of revolutions that the wheel makes and the linear distance or the straight line distance that the circle or wheel travels. We try here to illustrate this as best we can. What we've done is we've sort of pretended to wrap a rope or a thread around this wheel. So that's what that gray line is, that's sort of outlining the wheel. And you can see here the wheel has made 1/4 turn, and then a half turn, and then a 3/4 turn, and then a full turn. And of course, a full turn, that is known as 1 revolution. So what's happening here is that thread that we wrapped around the wheel, that rope that we wrapped around the wheel is unfurling as the wheel rolls along the ground. So you can see when the wheel starts, the thread is all the way around the wheel. But when the wheel has made a 1/4 turn, you can see that a 1/4 of the thread, there's a 1/4 of the thread, is now along the ground, and the other 3/4 is still along the wheel. Half turn, of course, you've got half of the thread on the ground, and then half is still wrapped around the wheel. 3/4, there's the 1/4 of the thread still wrapped around the wheel, and the other 3/4 along the ground. And then finally, when the wheel has made 1 full revolution, that thread is completely unfurled along the ground. Well, this distance from here to here is obviously, or should be obvious, that is 1 circumference of distance that the wheel has traveled. Why should that be obvious? Well, remember, the thread itself wrapped around the wheel, which means the thread itself must be equal to the circumference of the wheel. So after we have gone 1 revolution, the linear distance that the wheel has traveled is 2 pi r, or pi d. These two formulas are the formulas for the circumference of a circle. So again, 1 full revolution of the circle as the circle moves along a flat surface, a road, or whatever you want it to be. As we move along and we make 1 revolution, we will travel a linear distance, a straight line distance of 2 pi r or pi d, 1 circle circumference. So 1 revolution equals 1 circumference of linear distance. Let's take a look at one example. In this case, you might want to pause the video if you feel confident on these kinds of questions. If not, watch me work through it right now. This is a calculator question. I'm going to bring my calculator up just in case. Actually, let me put that down there while I read the question. A wheel travels along a flat horizontal surface without slipping. By the way, this language here, without slipping, they have to include that language in these questions, because if the wheel were slipping, the relationship that we just discussed, 1 revolution being equal to 1 circumference, would no longer hold. So that without slipping just means that this relationship is true, is good. If the wheel makes 410 revolutions and the center of the wheel travels a linear distance of 672 meters, what is the diameter of the wheel? I'm going to box this because we do have to round here. Nearest 1/10 of a meter. There's multiple ways that we could do this question, but I will tell you probably the easiest way is to set up a proportion. Remember that we know that 1 revolution is equal to 2 pi r or pi d. I'm actually going to be using the pi d formula here since we need the diameter. So 1 revolution is to pi d, and that must be equal to the relationship given in the question, that 410 revolutions has to be equal to a linear distance of 672 meters. So now, if I cross multiply and solve for d, I will have the diameter of the wheel. So that's what I'm going to do. 672 times 1 is, by the way, this really should have meters written there just so that we're writing all of our units like we're supposed to do in a proportion. So 672 times 1, that is 672 equals 410 pi d. And of course, I am going to do that in the calculator. There is no way I can do that calculation in my head. I do have to be very careful here. Some students will make this mistake where they do 670, that's supposed to be a 2, 672, so let me do this. 410 pi, we're dividing both sides by 410 pi. Some students will do in the calculator 672 divided by 410 times pi. The calculator will do this, but this will not be the correct answer, because what your calculator will do is it will do that division, 672 divided by 410, and then multiply by pi. So you can do one of two things in the calculator to make sure you get this correct. One is we can do 672 divided by, and then put the denominator in parentheses, 410 pi. That would work. And we get d equals 0.52. The other way that you can do this, if you have a TI-84, a preferably newer version of the TI-84, is you can go into your alpha F1 or alpha Y equals menu and use the n over d function, which will set up a nice, neat fraction for you so that you can just do 672 up there in the numerator, 410 pi in the denominator, hit enter, and then you don't have to worry about any careless calculation mistakes. So 0.521, blah, 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 521, blah, 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 but they ask us to round to the nearest tenth. This digit is a 2, which means we stay at 0.5. In other words, we do not round up to 0.6. So our answer is going to be 0.5 here. This diameter, the diameter of this wheel, will be half a meter, 1/2 meter. So that is how we handle questions that deal with revolutions and linear distance, as well as how we handle questions that involve points on a circle and the paths that those points take through space, or up and down around the wheel. Again, these questions are not all that common. When they do show up, if you know the information here, they shouldn't be too bad. We understand this was a long section. There is quite a bit to know in terms of circles. Circles questions, as we said from the get-go, circles questions are not all that common, but there are various ways that College Board can test circles. And if you want to be successful on circles questions, you're going to need to be familiar with all of those ways.